道都还有一个一，对，我不知道。7年级 ，OK， 我都算错了。没有，下面前面的肯定是18。对呀，烧铁。
最小，就是你们那个茶室的那个玩意模式。去跑步。那也就是你们第一次来还没有开始改。那现在能知道分吗？我没感觉。啊，这个你们都分过吗？
对啊。
对他没有分过。但我有个疑问，就你当时不是就是有些新的文件，那时候不是有些新的文件，把它覆盖到那个我们写的第一次上去。但是我发现你覆盖上去以后的话，它那个就是它原来有一些能过的就过不了，它 它是那个，它不是 Untitled，是说它编译。对，就是说它是这样，你打开，你能不能现在打开一下它那个 W 的那个描述？就是你往下拉，你拉到 X 开始，它这里这个是 bar 2嘛，它是改了 bar 2，它这里写的是 at this point，就是说你把这个改完了以后，你就应该能够过去。但是实际上就是说，就我在做之前，我就去跑这个，那当然是可能是不会过的，对吧？但问题是在跑这个音乐之前，它先编译了我，因为它导进这样子，先导进去的有一家区的。因为它是本身编译差不多，但是这样的话就是说，那我也就只能就是按照它顺序来做这个，我必须得先做这个去，要不然的话我不做不下去，它编译的不好。它编译的，它扛不下来，它扛不下来，它根本就不会去管你的那个音符。我的意思就是说，它这个实验没有因为后面做，它要先做下去，我才能这样子。因为如果你编不下去，它编译不对去，你新加一个编，就是原理还是这个东西，这个是它这个测试本身可能不好，但是如果你不做下去，你这个整个工程就编译不对，它这个编译工程它不能跑下来。就很就这次的话，你就没办法。他说改这个我知道，但是他到底哪些是哪些不是我也不知道。所以我觉得这次挺模糊他这个描述的。后面做。还没做到，我今天不对，但是我一做这个开了嘛，那个好，而且已经在录了。
Anyone have a stapler with you? Anyone with a stapler right now? No? Well, give us with a Google stapler. Then we will stick it. Yeah, do that. Yeah.
Yeah, I wasn't really sure which of these was supposed to be, so I ended up doing 2 to the 6 times by 2. I would
let me go over the okay, let me first go over the solution for hello. Hello. Did it work? I don't know what happened to this, so I will just, I guess I just speak louder today. Okay? So let me go over to solution briefly with you. I have already released this on the class homepage. Problem 1, the first 3 are fairly straightforward, right? The problem 4 and 5. So problem 4 really is a warm-up for you to work on problem 5, essentially. And to read the first 100 pages, what you do is you pay you to the start of the first page. Meaning align the head of your arm to be right above the head of the first page, top of the first page. Of course, plus the rotation delay, right? So this is to account for the rotation delay, and this is to account for the seek-time delay. Okay? And then finally, you need to wait for those 100 pages to rotate over the head of your arm. To capture that, you basically look at pages a track has. In this case, we have 125 pages in a track. So you simply use 100 divided by that. That gives you the portion of time it takes to rotate. The time to. So that's essentially the time you obtain here to read 100 pages sequentially. Any question for this? Now, once you understand this, the following 2 problems become fairly straightforward. For this query, right? Because you are doing a selection over the title of the class, and it's not sorted by the name of the class. So this essentially becomes a heap file scan. And you don't know how many matches you have to scan through the entire heap file in order to make sure that you have selected all the records, satisfying your precondition. Right? Any question on this? So essentially, it boils down to the time to read the whole file sequentially. That's essentially what this costs.
So are you reading the whole thing into memory and then checking each record?
Well, you read page by page, then you check each record, but we only count IO time. So even if you try to accommodate that CPU cost, once data are in the memory buffer, that will be dominated by this cost item.
Okay, but like if you read one page and then check each record on the next page.
The system control the reading of the page versus record. This will happen separately. Is something.
So if we did
CPU,
if we did the time for like random IO for
then it's not right. I don't think it's right. This is sequential rate, but this is not random IO. Okay. Of the table record. There was only one index. Okay. And then what happens at that leaf level with data entries using alternative to be fairly. Okay. Of course, that means that when you build your own database kernel, you can of course write your code in a way that I want to make sure all the pages are right around my desirable utilization ratio. Whenever it's above or lower than that, I will do split and insert, split and merge. But obviously that will become extremely expensive if you try to do that. The whole idea of utilization and deletion, enough room to support deletion on a given page, so that you don't constantly incur the expensive insertion and deletion operations on the tree structure. Okay. Problem 4 and 5. Once again, these are fairly straightforward questions. Once you understand what's linear hashing, what's extendable hashing, it should take you just a few minutes to hash out the tables. Yeah?
I do have one question about extendable hashing.
you
About which hashing?
extendable.
Okay.
So when you split a bucket, if all of those happen to stay, like have the same next bit, you then do it again.
You have to, let me repeat the question, make sure the class understand what the question is. The question was, in extendable hashing, you will split a bucket when it's overflow, right? Because extendable hashing allows no overflow at any given time. So whenever there's overflow, I will split that by increasing the local depth of that bucket. And if the local depth becomes larger than the global depth, I will have to double my global directory by increasing the global depth by 1, and so on and so forth, right? That's what extendable hashing is. And the question was, what if after you have increased the local depth by 1, and all the ends on that bucket still cannot be distinguished by looking at one more bit? In other words, they still result in increasing the local depth. So the worst case happens when all of them have almost the same bit for the lower ordering positions. And you have to go all the way to some really significant high order bits in order to distinguish them. Right? When that happens, yes, you're really unlucky. You're stuck with these guys that result in an overflow. You have to keep increasing the local depth until you reach a high enough significant bit to distinguish them into two bits to resolve the overflow buckets, right? And the consequence of that is you have this one local depth that matches the global depth value, but most other buckets' local depth value by now are way smaller than your global depth. In other words, you're creating a lot of overhead in your global directions, more than necessary to index the number of local buckets you have. But that's essentially the drawback of extendable hashing. That's precisely the motivation for people to design linear hashing, which is not to be so aggressive when addressing overflow buckets.
So is that extendable hashing when you can't have duplicates? Because if you had duplicates, then you could get too many and you could never.
Well, that's a problem for any hashing, not necessarily only for whatever hashing algorithm you come out with. If you, in an extreme case, if you have n values, all n of them are identical, what can you do? Unless you are willing to go with the randomized hash function, any determinist hash function will hash them to one bucket, no matter how smart you are in designing your hash function. If I give you n duplicate keys, what do you do?
Yeah. Well, I'm just saying with extendable hashing, though, you can't keep doubling forever, right? Because extendable hashing, like, you don't eventually get to a point where you just put in a linked list. You just keep.
Well, if you don't have duplicate keys, eventually, if you keep increasing the local depth, they will be distinguishable because they're
Okay, I was thinking that you could have.
yeah, but my point is, when you have duplicates, any hashing will suffer, right? Not necessarily just extendable hashing. All right, so, and typically one technique people use to address this is to use something called geometric perturbation, which is, so if I have a sequence like that, and assuming I have like a million threads here, if you want to use hashing to index them somehow, typically what you do is you have to increase your domain range, and we add some perturbation to this, something like that. So we add a small value so that, of course, you cannot add a value that's big enough so that 3 become after 4. You have to preserve the ordering. As long as you preserve the ordering, you add a small, this is what we call a small perturbation to do this. And later on, if you want to find a query point equal to 3, what you do is you change that to a range query. If you have to remember the perturbation you have done, change this to a range query of between 3 and 4. So a point technique. That makes sense? So that's one typical trick people use to handle the case when you have large amount of duplicates. Or if you don't care about the value 3 itself, not some associated values, then you can convert this to a count pair, right? That's another way to address it, but this has the problem of you can no longer distinguish these threads if each of the threads is associated with some other values that you do care about, then this counting approach doesn't really work. Okay, last problem. This problem is fairly easy to prove, actually. So, if you understand what universal hashing is and K universal hash family is, if you don't understand the basic concept, of course, this will be extremely difficult to prove. But once you understand it, it's actually fairly straightforward. Now, let's look at the first one. And the first one is basically the somewhat hardest one to prove among the three. Once you prove the first one, the remaining two can be built up based on the proof of the first one. So what's the input? Input is K universal. So first of all, let's read K universal is a family of hash functions. Okay? The size of this doesn't really matter. Okay? I have no restriction on the size of the family. And any hash function from H must be a mapping from a universe U, a domain of this. By the way, when I write it like this, it means it's from 1 all the way to H, right? And technically the size of your domain, so in other words, you can view U equal to basically this. U essentially is this domain, right? So that's the setup, right? Now the requirement is for K universal that says, if you look at the probability where the random choice is made, this is where whenever you define probability, you have to define your random choice, and probability is space, right? Keep that in mind. So whenever I write probability, I have to first define what is my random choice and probability space. In this case, my random choice is made over which hash function. Okay? And what it says is when you randomly choose a hash function H out of this hash family, the following must be true, which is must equal to this. No less than, no greater than must be exactly equal to this. Of course, I have to quantify what are x1 and a1 to ak. x1, x2 from xk are all from, okay, let me write this forward. From this domain, and okay? So there are distinct K values from your output domain. You randomly select K values from your output domain.
Isn't it
this?
the universe?
Huh?
Isn't it from the input?
No, from the output. Oh, yeah, from the input. All right. Okay. The AI or alpha I use in my proof must from the output domain. But a key piece of information is, for the output, I have no requirement on this. I do not have this requirement. I do not have this requirement. This turned out to be critical in proving this claim. So I have to have randomly K distinct input values mapped to K output values, not necessarily distinct. In other words, they can map to same values, or some of them map to same values, or none of them map to same value. All of these are fine. In any case, this must be true. In that case, I call this definition. I define this, right? I define a cat as cat. You can argue with me against that, right? This is just my definition. You follow me? Now, with this definition, I want you to prove if this shows that H is K minus 1 universal. First of all, what do you mean by K minus 1 universal? Well, simply change this to K minus 1, right? Does that make sense? And how do you prove this? Well, the argument is, let's look at this problem. We choose K minus 1 these input values, and they map to some K minus 1 output values. Not necessarily all distinct. What's this probability? Okay, here is the trick. This probability is basically equal to as capital Y, this whole thing, and Y, okay? And I do a summation of B from the output domain. And I choose a y, small y, from the input domain such that y is not the same or doesn't belong to this set. That doesn't belong to the first k-1 key value you have selected. So I randomly choose such one y. And this y, if I look at hash of y, this can obviously go to any output value, right? Do you agree? And this b can go over any possible values. Does that make sense? Yes or no? M of them. Do you agree? Must be M of them, because when b is chosen from this, so y can be hashed to essentially any of this value. You don't know which one it's gonna hash to, but it will be one of them. It cannot be anything else. Do you follow me? And what is this? If you think about this. And this essentially is n of them. Each of this has a probability of 1. Each of this is precisely, if I may change this back to the k universal claim, this y has k-1 terms, and this has another 1 item, right? So altogether they form a k distinct values, and together that's exactly this form. You follow me? So each of this has a probability of 1 over m to the power k by the definition of k universal. And you have n of them, so the whole thing is n of you have n such terms, you sum together, that's it. By the way, why I can do the sum hash to this output, but the probability of them essentially equal to, you consider one more hashing of another input value and sum over all possibilities. Does that make sense? Right? So that's why it's equal to sum of this. So that's the first proof. And once you understand the first one, the second proof is, okay, any question on the first proof? Huh? Good? Okay. The second question says, prove that once is k universal, so I'm going to use this, okay? Okay, so some of you are still puzzled, right? So let me show you. So when I say I have a short in my, I don't know, let me, it's better to do something else. Let me see, how do I prove this argument? Okay, let's say I have 3 items, 3 input, right? I say the first one is hash, I have 3, okay, these are my input values. I say the first 2 hash to these 2 guys. Okay? And the third one has many possible outputs, including these 2, and this and this. I want you this and this equal to this. But I tell you any 3 of them hash to this has this, and this has a probability of m to the 4, right? Output domain is 4, right? Output domain is 4. Does that make sense? Yes or no? Let's say I have. So what I do is, if I try to quantify the probability of these 2, what I do is I consider the last one equal to this, equal to this, equal to this, and equal to this. All the possibilities. When I sum up together, that essentially gives you, because essentially what you're saying is then the last one has no freedom. When you sum up all the, that's equivalent to say you only have k-1 random variables, even though on the right hand side you have k random variables, but when you sum up, when you force the last random variable to take over all possible choices, you sum up all the probabilities, That's essentially saying the last random variable has no choice, has no freedom. Essentially, you have only k minus 1 random variables. Okay, that's the idea. Now, problem 2. If it's k universal, I want you to prove that it must be. Of course, random choice is still here. This must be this. How to do this? First of all, you have to understand what is given and what you are required to prove, right? Before you attempt to show. The argument here, actually, once you prove the first one, it becomes easy, right? From k, you can go k minus 1. From k to 1, you go k minus 2. You can go 1, right? And this is essentially 1 universal. And proof. That's it. Right? Repeatedly apply the first argument until k equals 1. And this exactly this. If you have this implies both bidirectional. This means that h is 1 universal. But by the first claim we have just proved, you just repeatedly apply the argument until k equals 1, and you're done. So this is a fairly easy proof. Backward doesn't work. 1 universal doesn't give you 2 universal, because if you go this, claim is stronger. If you go down, claim is weaker. Okay, any question on this? The third proof, H is universal. So first of all, we have to understand what's universal, right? So what do I mean by H is universal? Strictly weaker requirements than any k universal hash family, even when k equals 1. Actually, that's the purpose of this proof. Let's recall what's a universal hash family. When you have no k in front, 1 or 2 or 3, no k in front. What's a universal hash family? Well, you also have an H. The setup is the same. And you have input domain U and output is M. And the universal hash family says H probability. Okay, random choice over the hash function for hx equal to hy. The probability of clearance for any xy from the input domain must less equal than 1 over m. You follow me? Now after seeing this, what I want you to prove is that if h is k universal, for some k equal than 1, then h must be universal. How do you prove this? Well, first of all, I use this argument. If it's k universal, it must be 1 universal. When it's 1 universal, this implies right? Which also means right? So the probability the equal actually is what? Which is so and a proof. So it must be universal, right?
So is one universal the same as?
No, 1 universal is stronger than universal. That's exactly what's showing here. When you have 1 universal, the clearing probability is this, actually much less than universal. That make sense? Yeah.
So by the definition of universal, we have probability of hash of x.
Oh, actually, I'm right. I think I made a mistake. That's a good question. So before, sorry, actually, 1 universal is still my earlier claim is still true, but it's subtle. So I have suddenly realized a small mistake in my proof. Okay. So this shows you the clearance for a value A, but you have n possible clearance. Yeah, n possible output. A can be any one of the n values. So the clearance probability is actually this, which equal to this, but still satisfy the universal requirement of one less than n.
So is it just that one universal is stronger because it equals 1 over m, but universal can be
Well,
less than?
I think I have to take back that stronger. Stronger is not necessarily well defined. Stronger in the sense that it gives you this property. Right? A universal doesn't give you this property. So that's what I mean by stronger.
Is universal?
Universal only
can be
gives you
less
the
than?
clearance probability this, but it doesn't tell you what's the probability of hashing to any one output value. Does that make sense? But one universal actually go further than not only I give you this condition, but not less equal than, it's equal than. So it's hard to say which one is stronger, because if you look at this sense, universal, you can argue the clearance probability actually can be potentially smaller than one universal. So in that sense, this is stronger. But if you look at, if you want to quantify the universal, doesn't give you that. So the subtle thing over here. I made a small, so there should be this alpha, remember, is a random choice. So yeah, m such random choice. So this proof has to multiply with m, so that gives you 1 over m. That make sense? Yeah.
This may just be a simple assumption you're making, but when you have the probability of 2 events, meaning you have an and symbol, is that equivalent to the probability of one multiply the probability of the other?
No, only if they are independent.
Oh, okay.
So only if we're independent, right? So or if you don't want to use the one universal argument, you can use k equal to 2, which give you this. When you have k equal to 2 universal, what is this problem? By definition of 2 universal, this must be. So that's another way to fix it. Yeah. Okay. So that's essentially the homework. Now let's get back to our lecture slide. I forgot to book into Windows, so I will just use, which means we will use all the app, but I don't want to lose time to reboot into Windows OS. Right? So let's just go with the PDF app. Okay, so last time we talked about external sort. Oh, the other thing I want to highlight is that K universal hash family is very useful construct because K universal hash family give you what? Give you K-wise independence. Okay, this I never proved this way, but take this as an argument, right? Actually, you can try to prove this using the 3 claims we have proved. It's not hard to show this is the case. What do I mean by K-wise independence, by the way? So 2-wise independence is basically this should be when you have 2-wise independence, only if you have okay, only if there are 2-wise independent you have this. But 2y's independence versus 3y's independence, to argue that, to reinforce my earlier argument that K universal hash family is strictly stronger than K minus 1 universal hash family. One way to look at that is to look at Ky's independence. Ky's independence is always strictly stronger than 2y's independence, K minus 1y's independence. Okay? So I will give you an example. I think I gave this example during lecture time. I don't know whether all of you fully understand that, but let me repeat that example, which is, if you look at x and y, and their domain is just 0 and 1. Okay? Both are random variables with output domain from 0 and 1. What that means is, right, each of these happen with half probability. Because each take value from 0 and 1 uniformly. So each is equal to 0 with probability half, equal to 1 with probability half. If x and y are truly independent from each other, meaning they're the output should be just the probability you have this is 1 over 4, so on and so forth. Right? And when that happens, that's give you exactly what? 2y's independence. But the example I give you in class is that consider another random variable z, which also take value from 0 and 1. Which also take value from 0 and 1. And z is defined as S exclusive of 1. Is that okay? So obviously the output, because you are exclusive of 0 or 1. Do you follow me? What's the output? Can someone help me fill in this table here?
0, 1, 0.
0, 1. Right? If you look at z itself, forget about x and y, just look at z. What's the probability z equals 0? Half. What's the probability z equals 1? Well, also half. So in this sense, if I give you just z or x or y without telling you which is z, which is x, or which is y, you have no way of distinguishing them. Because no matter how many trials you do, no way you can distinguish them. They appear the same to you. Do you follow me? But the probability of in this case is what? It's 1 over 4, right? Do you follow me? If they're truly independent, what's this probability? Suppose I have another z prime, which is same as x and y, does not equal to the exclusive all x and y. What's the probability that all of them equal to 0? 1 over 8. Excellent. Rather than 1 over 4. Right? Because when you have 3 values, you fill out this table, the table looks like, when you truly have 3 random variables, the table looks like this. So this is 1 over 8. That equal to times, which is half times half times half, that's equal to 1 over 8. That shows you the 3 are truly independent. Clearly that's not the case here. This is a perfect example where there are 2 y's independent, but not 3 y's. What's more interesting, if you look at x I already argued for actual x and y are pairwise independent, right? What about pairwise independent? In this construction, right? Where are they pairwise independent? Someone?
Yes.
Let me ask someone else. What about you?
Yes.
Prove for me. How do you prove they're pairwise independent?
Because put x equal 0, and z could be 0 or 1, and therefore they both are
No, I don't like the argument. That's kind of a fuzzy argument, right? To prove they are independent, first one you make ignore y. Ignore y. Right? 1 over 4. There is 0, 0, 0, 1, 1, 1, 1, 0. And what's the probability? And proof they're pairwise independent by definition. What about y and z? Same, right? So this is an interesting construction where any two of them, but when you look at three of them, they're not three-wise independent. This shows you k-wise independence is strictly stronger than k-1-wise independence. I don't prove. Whereas in this case, when z prime is not this, but z prime is just one value chosen from 0 and 1, any two of them are pairwise independent, and any three of them, you only have one combination of three of them. Three of them are also three-wise independent. So this is three-wise independence, and this is only two-wise independence. And you see that three-wise independence, automatically you will have two-wise independence. Okay. So that's enough.
So there's nothing that's not one-wise.
No, independent. When I say pairwise independent, you have to have involved at least two, right?
Yeah.
Okay, so these are some really basic knowledge, right, about randomization and master computer science students. These are fairly basic things I do expect you to know. And if you don't know this before this class, that's okay. Now you should know, right? And if after this you still don't know, then you have no excuse, right? I don't feel comfortable signing off on a master program study for. A timely thing for this is election. Think about election, right? That we're going to have in November, right? It's all about randomization and how they do the poll and how they do all of these things. It's all about this, right? So a lot of polls they do, I bet they're not necessarily k-wise independent. I mean, the people they call are not necessarily k-wise independent. Right? For the entire U.S. population, if you do a poll of, let's say, involving 1 million people, then it should be 1 million wise independence, right? But you see why that's hard, right? As we argued, K universal hash family, how do you construct this? Well, right, if you try to make a 1 million wise independent hash function, what do? You have to raise the input to the power of million, and this becomes extremely expensive to compute. And that's why in practice, you don't have desire to have. They're just so expensive to construct. Yeah? And that's the reason why oftentimes people just settle for this, which gives you a 2-wise independence. Which already give you 2-wise independence. Meaning, if you look at any two of them, they are independent, but it's, well, once you look at three people they have called to do the poll, then there's some subtlety. You cannot trust the result that much. When you say the poll shows that the support for whoever is how much, there are always some correlations in the way they do it. Unless they're using a truly k-byte independent hash function to select, then typically that's a very expensive thing. Now, sorting, we talked about axial sorting. Okay, so now I'm going to show you some improvement. Right? So last time, did we talk about this? No, we haven't talked about this. We talked about the case of with only 2 pages, or 3 pages actually. So the idea is spend way much time than too much time on that. Okay, what we said is right? Remember that's what we said last time. We will have a run of sorted pages. During any pass, what we do is we load the first page from the first one and the first page from the second one and start merging them. Whenever this is filled, we dump to the output, and then we load the next page. Suppose I move the cursor here, and somewhere it is in here. I load the next page from the same run, and I start merging them until at the end of the day I have finished merging all of them. Then this becomes one run of twice as big in size. And if you do this, initially you start with how many runs? You start with, let's say, n over b, n is your buffer size, and b is your page size. Both are in terms of how many objects it can hold. How many objects you can hold in memory, how many objects you can hold in a page. So number of pages in the buffer is simply m over b, right? However, in the base case I show you with only, initially you have only 2, right, or 3 pages. So you sort them. In the first case, you basically load every 3 pages, sort them, dump to the output. In the first phase, you use all 3 pages. You do that, but in the extremely naive algorithm, you don't even use 3 pages. In the first phase, you just load 1 page, sort it to the output. So what you do is you start with n over b rounds. Right? Each page is run by itself, and you need this many reduced to a single. All pages by once. So that's the total idle cost, right? Now, what if you have more than 3 buffers? Suppose you have n buffers. Buffer size is n over b, which is greater than 3. Can you do better? Well, the idea is definitely you can do better, right? So here is what you do. In the first round, pass 0. You load n over b pages and sort them. You use the in-memory sorting algorithm to sort them. And then you dump to the output. What you get is a single run. How many such runs do you have? Well, roughly, you have n over b pages in total. The size of each run is n over b, so you have this many runs in total, roughly. You follow the calculation? That's essentially n over n. Of course, this might not be modular to 0 to each other, so you should take the ceiling of it. The last run, so all of these are n over b. The last run could be anywhere from from 1 to n over b. The size of the last one. Does it make sense? But in total, you have this many runs. Now, in the remaining pass, once you understand this algorithm, the remaining parts become very simple, right? What do you do? Well, you use one output page buffer. This is one page. How many remaining pages you have? You have M over B minus 1 number of pages left in your buffer, right? And what do? Well, you do the exactly same thing. What you do, now there's conceptually they look like this. Each of this is a run, and this of size 1 M over B, size M over B, size M over B. And the last one, the size is the value x in the range of 1 to M over B. Right? And how many such runs you have in total? We just did the calculation. You have in total N over M number of runs. Right? What you do is, so this is the view. You load the first page of the first run into the first buffer page. You load the first page of the second run into the second buffer page. And you load the M over B minus 1's run. So this must be M over B minus 1's run. So remember to skip any runs in between. Into the last buffer page, except the output buffer. So you have M over B minus 1 input buffer pages in total. And what do? Well, pretty much you do the same thing as you did for that 2 pages case. You push the smallest value pointed by one of these cursors to the output. Then you push 3 to the output, and you move the cursor, so on and so forth. Eventually, you will reach a state where it looks like somewhere like this, and the output buffer is filled. You dump this to the output, and then this becomes active, and you start moving them again. Completely exhausted. What do you do when that happens? Well, you load the next page from the same run. And we set the cursor here, and you start moving them. And at the end of the day, what do you get? You got a single run of merging these guys. So what's the size of that run? Each has M over B pages, and you merge roughly M over B minus 1 runs. So that's the size of this run. You follow me? So roughly is this. Do you follow my argument here? The size of each run is M over B, right? And you're merging M over B minus 1 number of runs. So that becomes this. In other words, and then you move on to the next M over B minus 1 runs. You're done with all of this. You move to the next M over B minus 1 runs. You start merging them. And what you get at the end of the day is multiple runs. How many runs you have? Well, remember you start with these many runs, N over M. And you merge M over B minus 1 runs into a single run. Does that make sense? So the total number of runs you get at the end of the day is essentially this. Take the ceiling of that. Because it could be the case that in the last session, you do not have M over B minus 1 runs to merge. You have less than M over B minus 1 number of runs to merge. Now, nonetheless, you still convert them, right? Just that be anywhere between, what's the possible value of the last one, the size? It's anywhere from 1 to what? M over B of this, roughly this. Right? So the last one will be anywhere from 1 to this value. But this is number of runs you have. And then you continue, right? If you do another pass, what happens? The number of runs is reduced by another factor of this. Because every pass, you basically merge M over B minus 1 runs. Reduce the number of runs by this factor. So how many times it reduced to a single run? Well, that's the same as, remember in the basic case we do log base 2. Here we just simply do log base of this, because that's how many runs you are merging at each pass. In other words, that's the reduction factor every pass in terms of how many runs is reduced in each pass. And you start with how many runs? You start with N over N runs. And you need this value ceiling of that, remember? You have to take the ceiling of this. Because it could be that you are left with only 2 runs and you still have to merge them. Even though you can merge M over B minus 1 runs, but you only have 2 runs left, you still have to do another pass on merging them. So you have to take the ceiling plus that first phase, which is to get these guys. And in each pass, you read all pages by once, you write n pages. So the total I/O of each pass is just 2n. So that's your final value. Right here. Okay? Okay, so that's this algorithm. Okay. So 2n over b is the number of pages, right? The n is number of objects, number of records. N over b is number of pages. So here is an example. Let me give you a special example. So using this algorithm, you can basically sort 100 terabytes of data in only, let's say, 10 gigabytes of RAM. And fairly quickly too. Fairly quickly too. Even though n is, so it's really hard to. Let's say instead of, and you can sort that in mass. 10 gigabytes of RAM. Though you cannot load, but you only need to make several passes. Almost like linear. In practice, this is roughly viewed as a small constant. Cost is literally people just view sorting as linear cost. You make several linear passes over your data, terabytes of data they're sorted, no matter how small your RAM is. Like I can sort this, I can sort entire data using my laptop by making several linear passes over their data. Okay. And remember, the other cool thing about this algorithm is embarrassingly parallelizable, right? When you are merging this M over B minus 1 runs, you can start merging the next M over B minus 1 runs. This system. The first M over B minus 1 runs are merged together, but the next M over B minus runs can be merged using another node in parallel because they are totally independent. Does that make sense? And so it's very, this algorithm is very amenable to parallelization. Now, let's look at some special examples. Suppose I only have 5 pages in my buffer, and I have 108 pages to merge, to sort. What's the size of each one, pass 0, number of runs, and so on and so forth. We need to fill out these values. In the first phase, what I do, I load 5 pages, sort them. So the size of each one obviously should be 5. That should be fairly clear to you. And with 108 pages, how many rounds I should have? Well, I have 21 rounds of 5 pages. That gives me 105 pages. Then the remaining 3 pages go to a single round. So in total, I have 22 rounds. Alternatively, the calculation is simply like that.
So we're not giving a very long for the output?
In the first pass, you don't need that. In the first pass, you load 5 pages, you use all of them are output pages. In the first pass. But follow up to her question, in pass 1, you start seeing that effect. Now you cannot merge 5 rounds, you can only merge 4 rounds because you have to reserve 1 as the output buffer. You can argue, what if I don't reserve an output buffer? I want to merge 5 rounds. That seems to be more efficient. What happened in that case? Well, that's kind of like, remember the I/O efficient implementation of queue and stack. How do you do an I/O efficient queue or stack? We talked about this problem. You never push or pull. By doing that, you amortize cost over B item to become 1 over B versus B IOs. If you don't have this output buffer, then you are not looking at N over B IOs in the output. You are looking at, instead of N over B IOs, you are doing in the output, you are doing N IOs in the output without that output buffer. For this reason, remember the stack and queue animation I showed you before? So we do need to reserve the actual buffer page as output, and the effect of that. And with 22 rounds, and you merge every 4 of them together, that gives you 6 sorting rounds. And each round, by the way, once you merge them, and once you merge them, what it becomes is the following. It becomes, so each one is 5 pages. And you are merging 4 of them. Right, so the output is, right? And how many rounds do you have? Well, you have 22 rounds to begin with. You merge 4 of them into 1, you take the sitting of that will give you 6. 6 rounds. Why? 5 of them are 20 pages. The last one is only 8 pages. Why is that? Because you have 22 rounds from the first round, right? From pass 0, you have 22 rounds. And 21 of them are 5 pages, and I argue for you, the last one has only 3 pages. So this is essentially the 20th round, and you merge that. Single round of only 8 pages. And that's how you get, in this pass, at the end of this pass, you get 21 rounds. You got 5 rounds of this and a single round of this. But if you ignore all the details, the simple calculation is just this. That gives you 6 rounds. 6 rounds, and you move on to the next pass. Can you merge them? Not yet. You can only merge 4 rounds. So 6 rounds become 2 rounds. 6 rounds, let me finish now. So 6 rounds become 2 rounds. Each has 20 pages. So the first round has 80 pages. The second round has what? The second round, you're merging the remaining 2 rounds among the 6. One has 20 pages, one has 8 pages. So the second round only has 28 pages. You're merging a round of 20 pages with a round of 8 pages. Okay? And then finally, you do another merge of 2 rounds. Even though you can merge 4 rounds, but I'm only merging 2 of them. 80 plus 28, that gives you 100. Okay. Do you have a question?
Just clarifying, I think you explained already, but you divided by 5 the first time, and then it's by 4 every time after that. 1 extra page.
Yes, for the output buffer. Yes. Okay. So here are some examples. When N over B is 10 to the power 9 as this is the number, by the way, this is the number of pages. So when you have 10 to the power 9 number of pages, with a buffer size of only 257, which is fairly small. If you think about 4 kilobytes, what value is that? That's only 1,000 kilobytes. And that's what? That's only 1 megabyte. When I have only 1 megabyte of memory, I can store. Okay, this is how much? This is 10 to the power 6 megabytes, or 3 megabytes, 4,000 gigabytes, so 4 terabytes a day. With 1 megabyte of memory, I can store 4 terabytes in 4 paths. With only 1 megabyte. Not even 1 gigabyte. Using only 1 megabyte from my computer, I can store 4 terabytes in 4 paths. I linear scan it 2 times. That's it. If I increase this for 1 gigabyte, meaning instead of 257 pages, I have this many pages. That's 1 gigabyte. Right? That's 1 gigabyte. Then I can sort them by probably just 2 paths. That's how powerful this algorithm is. And that's how Google and all these companies do their sorting. Of course, unless they have sufficient memory, then you load everything you sort. Period. I know. You don't do this. That's just one I/O. Of course, if you think about it, you try to dump the output, consider that. That's only over B, right? Read and write. And you do sorting in one pass using a in-memory algorithm. But my point is that requires you to have 4 terabytes of RAM. Right, in this input. I cannot afford that. I don't know about you guys, I cannot afford that. That's a lot of RAM. And not only money is one thing, the physical property of RAM actually doesn't allow you to have 4 terabytes on a single node. Right? CPU, if you have taken an architecture address to certain memory space. Right? Like a lot of i7 CPU can only address up to 64 gigabytes RAM. Even if you are willing to pay 128 gigabytes, you are as rich as whatever you want to pay, whatever. Sorry, even if you are willing to pay, we cannot offer that service. Okay, so that's essentially the basics of XML sorting. Now some interesting tweaks. Interesting tweaks is the following. Okay, the first interesting tweak is the following: is that okay, here is the interesting twist, is that if you use the algorithm we just described to sort input file, the output is what? The cost is what? Right? That's the, of course, that's one. Okay, that's the cost. That's the cost. Now, what is the worst case for this algorithm? Worst case is you have a file that has n over b pages, but it's already sorted. It's already sorted. You run the algorithm we just described, what will happen? You still need to take this many IOs to guarantee, quote unquote, guarantee that it's sorted, even though it's already sorted. But of course, you don't know this fact, right? If you know it's already sorted, then why you're doing this in the first place? You don't know it's sorted, but actually it is sorted.
Does that just happen with any sorting algorithm that you have?
Well, that's the trick I'm going to show you next time. A lot of sorting algorithms either improvement, like for the quick sort, for in-memory data set, right? For in-memory data set, you use quicksort is n log n, right? Now b is no longer a factor, right? Just n log n, the running time. But if it's sorted, if you know it's sorted, to check something is sorted only takes linear time, right? You simply check each value against the value before it. As long as you find anything that's out of order, then you stop, right? To check something is sorted, it only takes linear time. So if something is sorted, intuitively you should only spend linear time. Anything more than linear doesn't make any sense to you. But if you just use quicksort blindly, on expedition you end up with n log n. Can we do better in those cases? Right? So here is a trick. Here is the trick. The same trick applies to internal memory algorithm too, right? But let's see the algorithm. This algorithm is described here, but I'm going to use this. You can look at the pseudocode. The pseudocode is fairly short, but to understand this actually is not that trivial. So instead of going over the pseudocode, I'm going to use this animation to show you what happens. Right? Called tournament sort. Tournament or playoff. Right? So what the basic idea is this, right? You want to check among this team. Imagine we are a bunch of soccer teams or football teams. I want to test which one is the best football team. Right, either Florida State or Utah or BYU or Ohio State or Wisconsin. Right? If you watched football game last week and you know for sure Wisconsin is weaker than Ohio State. They just lost to them. That makes sense? So a simple idea we leverage here in tournament sort is we will have kind of like a gatekeeper, and every new team will compare against this team. If you win against this team, you go to the winner club, and then they will compete against each other. If you lose, you go to the losers club, and then you guys compete against each other. Because if you lose against this team, and this team lost to the winner club team, there's no point of playing against them, right? And that's the simple, I mean, it's more complicated than this, but that's roughly how the playoff ranking is ranked, right? If you lost to somebody, you cannot rank above that person, obviously, right? So that's essentially the idea here, right? So what we do is the following. We have this many pages, right? M over B. What I'm going to do is I maintain two heap. Remember, these are not heap files. These are main-memory data structure heap, meaning they are sorted. It's essentially binary tree. That's what I mean by heap. Okay? I maintain two heap, H1 and H2. Initially, they are all empty. So two empty binary. So this is H1, this is H2. And one is the winner, one is the loser, essentially. The winner club and the loser club. N over B pages, right? So what I do is the following. In the first step, I simply load M over B pages into the main memory and sort them. I load M over B into main memory and sort them. Is that okay? I sort them. Then I push the sorting to the, I leave only one page, of course. I load M over B minus 1 pages, insert them into H1. So this now has M over B minus 1 pages, but they are sorted, right? Heap is a binary tree, it's sorted. Now I load the next page, which is M over B page, into here. And what I do, to make it precise, so I have to initialize H2 to some size. Okay, H2 here, I use one page for the input buffer. So H1, H2, this is the input buffer. Some constant. One input buffer, one output buffer. I load the next page in. What I do? If the next value here now is in memory, right? So I'm going to turn a cursor and check each value against the largest value from H1. The largest value against H1. If it's larger than the largest value in H1, what do? I push to H1. If it's smaller than the largest value in H1, what do? I push to H2. So X against from H1. I call this value V. If X greater than V, X goes to H1. If X less than V, X goes to H2. The equal case, we go to H1. Okay? And then we start pushing output to the output buffer from H1. We take the smallest page from H1, push to the output buffer, and dump them to the output. And then this process continues. When you run out of input buffer, you load the next page. When you don't have space, you output one page from H1. And when do you terminate? When you have no item left in H1, in has nothing to push to H1. What do? You reset. Now you reset. You start a new round. And you start pushing to the output. And by the way, when you reset H2, the content of H2 becomes H1. That's the initialization of H1. And then the whole process recurs. If you think about why this works, if the whole thing is sorted, the next page you bring in always going to have value larger than the max value of H1. So essentially, you sequentially load everything, you sequentially push everything. What's the worst case of this algorithm? The input is inversely sorted, from the largest to the smallest. Then you load the first round H1. The next page you load has no value larger than the next value in H1 because it's inversely sorted. You have to push the entire output of H1 to the output and start the next round. And each time you reset, the previous output define a round. So in the best case, the size of run is n over b, which is the whole file is sorted. The worst case is what? It's roughly b minus 2 or b minus 3. This constant, right? Basically, it's inversely sorted. You load b minus, sorry, n over b. Yes. Yeah, n over. Right? B. You load the entire thing sequentially right to the output. You never reset. The worst case is inversely sorted. You load n over b minus 3 roughly this many pages. Then the next page you load max value of these guys. You cannot push anymore. You terminate that one round. You start a new round. So this is the case. On average case, people have proved this. I'm not going to prove this for you. This algorithm will produce a round of roughly this size. On average. On expectation, it will produce a round of this size, which is the basic merge sort algorithm we use, which only produces m over b. The size of the round in the first pass 0 is m over b. But now we can double that. When you double the size of round in pass 0, what that means? That literally means you reduce the number of rounds in pass 0 on expectation. And you are still merging same number of rounds in the subsequent passes, but you start with less number of rounds. What that means? The whole algorithm becomes more efficient because you are using less number of passes to merge them. Okay, so this is this algorithm. Okay. With that, I stop right here. I will continue next on Thursday.